Well, before we start looking at the circle theorems, I just want to remind you of the terms that you've probably come across already, but maybe there's one or two that you haven't. Okay, here is the circle, the center obviously. Now this doesn't move, and the edge is the same distance from the center all the way around. So if we draw a line from the center to the outside, this is called the radius. And with this fantastic program called GeoGebra, I can move the radius round and you can see that it remains the same length and it acts like the compass point that draws the circle. So there we are, the radius. Now, if we go right across the circle from one point through the center to the other side, this is called the diameter. And I'm sure both the radius and the diameter and the center, you've met all those terms before. Now, the two terms you might not have met before is this blue line here. Now, this is called a chord. And what a chord is it can be a line within the circle that join any 2 points. So I can move the left-hand arm of the chord here or the right-hand arm, all the way around. And it can be as tiny as you like, or it can be the same length as the diameter if I put it to the opposite side of the circle. Okay. The other term you might not have come across is this line here, this yellow line here, which is called a tangent. And what a tangent does is it just grazes the circle. And I can move that point round the circle and you can see what the tangent does. So once again, this fabulous program, GeoGebra, can demonstrate this really very, very well. Now, the only other term that you need to know about before we move on to the theorems themselves is this word subtend. If I set two lines on either end of the chord we've set up, and those two lines join at the opposite side on the circle itself, there will be an angle between these two legs, if you like. And the technical term used is called subtended. The angle between the lines is subtended on the blue chord. I rather like the word stands on, because if you can imagine these are legs of some bipod, do you see? The legs stay on the chord and I can move around the circle. And actually, one of the theorems says that angle remains the same, and that's the theorem we're about to come to. But you see, look, I can move the chord round to anywhere I like, and that angle then is still subtended on the chord. So subtended can be equated to stands on. Okay, let's move to the circle theorems themselves. So here's the first of those theorems. It states that the angles subtended by the same chord within the same segment are equal. Okay, well, it's really as per the demonstration I've just given you. If I move this point round the circle, you can see that 76.5 remains the dimension or the value of that angle, because the angle is subtended on the chord and the chord hasn't moved. If I move the chord, yes, the angle changes its value. And I can do that with the left-hand arm of the chord or the right-hand arm. But once set, moving this around, that 46.7 value there remains the same. And that, of course, means that if you've got multiple angles subtended on that same chord, as in this diagram, and the angle between the pairs of lines that are all standing on that chord, the angle up here between the two legs is the same. And they'll all change together if we change the chord. Okay, theorem 2. We've still got that angle subtended by the two white lines to the opposite side of the circle, but we've introduced two new lines, this time to the center of the circle. These green lines, of course, are both radii. And if you look to the maths that the diagram has shown you, 60.7, if we double that up, yes, we get to 121.5. So the angle subtended to the center from that same chord is double. So yet again, if I introduce some animation, here I go. If I put the middle angle to 100, and there you are, the angle on the full subtended lines to the opposite side of the circle is 50, and the angle subtended to the center is 100. Yet again, I'm still able to move those around, and the angle 50 doesn't change. But as soon as I move the chord in any way, they both change, but they're linked by a factor of 2. Okay, let's move to the third one. Now, in a way, what we've done is we've taken that blue chord and turned it into a special chord called the diameter. So this splits the circle into 2 semicircles. And if we subtend 2 lines on that diameter, the angle between the 2 lines is 90 degrees. And it's always 90. I can move this point around, and it remains a right angle. And I can move the diameter around, and it also remains a right angle. So that's theorem number 3, that the angle subtended on the diameter is a right angle. Okay, number 4. Now, we've got 2 radii, and at the point that the radius hits the outside of the circle, I've drawn a tangent. So we've got 2 tangents and 2 radii. And the theorem says that the radius and the tangent meet at a right angle. So we've got a right angle here where this radius meets this tangent, and we've got another right angle where this radius meets this tangent. If I draw the center line, we've got 2 right angle triangles, really. Here's one of them, and here's the other. Now, they share the same hypotenuse, and these sides are equal because they're both radii, which means that this side must equal that side. The triangles are similar. It also means that this angle, if that's theta, there's another theta there. And if this angle is alpha, this is also alpha. So you've got a fantastic symmetry around there, and a lot of questions exploit that fact. So as soon as you see tangents meeting at a point, expect a lot of equal length sides and equal angles. We're back to using a chord with this next theorem. And we draw from where the chord touches the circle to the center, we've got 2 radii. And if I drop a line from the center to the chord, the angle between that line that I've drawn and the chord is a right angle. It also means that it split the chord into 2 equal lengths. In any quadrilateral, in other words, 4-sided figure, the internal angles add up to 360 degrees. That's true of a square, a rectangle, or any irregular quadrilateral you can draw. The internal angles add up to 360 degrees. Now, if we position that quadrilateral with its corners sitting on the circumference of the circle, then yeah, we haven't changed anything. All the angles still add up to 360 degrees. But an extra thing happens. This pair add up to 180 degrees, but so does this pair. They also add up to 180 degrees. 68.4, yeah, okay, and 65, yeah, both do. So let me animate this diagram for you. I can move that corner around. And actually, if you imagine a blue chord between those 2 points, the angle is subtended, and you won't be surprised as I move this point around, it doesn't change. Yes, the 2 green angles change, but they lock themselves together to add up to 180 degrees. And I can do that with the green one now. Now the green angle 92.6 doesn't change, but the 2 orange angles, one increases as the other decreases. I think you can see that rather well there. I can move this one around. Now its own angle remains the same because effectively it's subtended on the invisible chord between these 2 points. So its value doesn't change, and moving it causes one of the green angles to increase and the other green angle to decrease. So that's called a cyclic quad, and that crops up in questions, well, really very often. So this is a good rule to remember. Now I think we come to the most obscure of the theorems. I've got a chord set up here, and I've drawn a tangent to the point where the chord meets the circle. And there is an angle here, it's saying it's 59.1 degrees, between the chord and the tangent. Now on that chord, I've subtended a two-legged creature standing on that chord. And the angle subtended on that chord, it turns out that it's equal to the angle between the chord and the tangent. I think it's probably least obvious because it's the furthest away. Both the angles seem very unrelated. But of course, one of our construction lines that we've used is a chord in itself. And it also has an angle here between itself and the tangent. Where is that angle? Well, it's the angle subtended by the two lines standing on that chord. So the angle here is another theta. So we've got a double pair of equal angles.